All right, let's take a look at our third example problem from Chapter 6. Steam enters a cooling tower at 200 degrees C and exits at 60 degrees C. Cooling is supplied by the surroundings, which are assumed to be at 30 degrees C. The process takes place under atmospheric pressure. Okay, and we're asked to calculate the amount of heat removed from the steam, calculate the entropy change of the steam, and then we're asked what is the entropy generation. All right, so let me try and draw a schematic of what we have going on. So I'm going to draw my device here. So I guess this would correspond to my cooling tower. I'm going to have some inlet to my cooling tower, which consists of steam, okay, at T1 of 200 degrees C. And then we're told that this is taking place at atmospheric pressure. So I'm going to take P1 to be equal to P2 to be equal to P of the surroundings of 1 bar. Okay, coming out, I'm going to have an exit stream. So now my steam's been cooled off. So now I'm at 60 degrees C. And then P2 is still going to be equal to 1 bar. Okay, so I know that at 1 bar or 1 atm, Tsat is 100 degrees C. So I know that in my entering stream, I'm going to have a superheated vapor. Okay, and exiting, okay, again at 1 bar, Tsat's 100 degrees C. So now I'm going to have a compressed liquid. And when we read data from the steam tables, right, our assumption is if I take enthalpy as an example, I'm going to assume that the enthalpy of my compressed liquid at T and P is approximately equal to the enthalpy of a saturated liquid at the same temperature, but at the corresponding saturation pressure, where P is greater than Psat. Okay, and that way I could read off my properties from the steam tables. Okay, so I have my inlet and exit. Cooling is supplied by the surroundings. Okay, so I'm going to assume that my surroundings I'll treat as a bath. Right, and so I'll take the temperature of that surrounding air or my surroundings. I'll call it T bath, and that's going to be 30 degrees C. Okay, and of course the pressure of that bath is also 1 bar. So we're asked to calculate the amount of heat removed, calculate entropy change, and entropy generation. All right, so I believe I have my picture fully labeled. And so, actually, let me do one more. Right, we want to calculate the heat removed. So let's go ahead and let's start with our first law energy balance for our open system, which we have here. And then hopefully we can use that to calculate Q, the amount of heat removed. We should be able to, since I know the inlet temperature and pressure and exiting temperature and pressure, so my system's fully specified. And then once we get Q, which we need an A, then we'll go and write our entropy balance and use that to calculate the, we'll calculate the change in entropy, and then C, we'll write our entropy balance to calculate the entropy generation. So all right, so I'm going to start with writing my general expression of the first law for an open system. Okay, and so I'm going to have du total dt, my accumulation term, okay, plus, not a summation, delta, okay, so using the notation from the book, I'm going to have the change in my kinetic energy plus potential energy plus enthalpy. Okay, remember enthalpy and not internal energy, because my fluid element needs to perform work to displace that fluid element in front of it. Okay, du total, right, that has units of energy, so U total has units of energy, so du total dt has units of energy per time. H here would be my specific enthalpy, say energy per mass, so I'm going to multiply it by my mass flow rate, mass per second, or mass per unit time, so that my units are consistent and work out. Okay, and that's going to be equal to Q dot plus W dot. So once I write down my general expression for my first law, I'm going to start by making assumptions. So the first assumption I'm going to make is that we're operating at steady state. Okay, so what this does for us is two things. Okay, that means the du total dt is just equal to 0. The other thing it'll allow us to assume is that my mass flow rate of my inlet stream is equal to the mass flow rate of my exiting stream, which is just equal to, just call it m dot, right, mass flow rate. Okay, so we're going to assume steady state operation. Okay, assumption 2 is I'm going to assume that my change in potential energy and kinetic energy is negligible. Okay, and so what that does for me is that allows me to kill these first two terms. And so, actually, let me make one more assumption before I write down my simplified equation. My last assumption is that we're not given anything in the problem to suggest that there's any sort of work interaction between my system and surroundings. There's no shaft work being done on my system. And so I'll assume no work, and the W dot is equal to 0. Okay, so with that, my first law of balance is going to reduce to H2 minus H1 times M dot is equal to Q dot. Now remember, Q dot is going to have units of energy per time, right? What we could think of as my extensive heat divided by, or extensive heat per time, right, a rate. So if we divide through by m dot, right, I get H2 minus H1 is equal to Q dot over m dot. Okay, energy per time, mass per time, that's just going to have units, or that's going to be equal to Q as we thought about it before, right, energy per unit mass. So just to clean things up, right, I end up with H2 minus H1 is equal to Q. Now, knowing that my inlet stream and outlet stream are fully specified, we can go to our steam tables, get values of H2 and H1, which we can use to directly compute Q. And as I go to the steam tables, I'll also get entropy, since I see I'll need entropy in B. All right? And then last point, again, before we go to the steam tables, is state 1 I know is going to be a superheated vapor, because at 1 bar, I know that my saturation temperature is 100 degrees C. So since my temperature is greater than Tsat, I have a superheated vapor. On the other side, since at 1 bar, I know that my saturation temperature is 100 degrees C, here I have a compressed liquid. So I'm going to assume that the properties of my compressed liquid are approximately the same as the corresponding saturated liquid at the same T, which in this case would be 60 degrees C. All right, so let's go to our steam tables and get what we need. Okay. So if I go to the steam tables, okay, I'm going to start out in the superheated steam tables. So my inlet stream, I have a pressure of 1 bar. Okay, again, saturation temperature is 99.61, and my temperature in state 1 is 200 degrees C. So I go over to 200 degrees C, which is right here. So H is 2875.5. Right, 2875.5. And then, and it would help, let me just, 200 degrees C? Okay, 200 degrees C, 2875.5. And S1 is equal to 7.8356. 7.8356. Okay, and this is kilojoules per kilogram. Kilojoules per kilogram Kelvin. All right, so now to get state 2, we said we're going to assume that the properties of a compressed liquid are the same as the corresponding saturated liquid at that T. So I go to my saturated steam tables. and I look for 60 degrees C. Okay, so we're assuming that it's 60 degrees C and zero point 0.2 bar, our properties of our liquid are the same as at 1 bar. All right, so I get H liquid, which is here, it's 251.5, 251.15. So 251, and S2 of my liquid, so that's 0.8312. Okay, kilojoules per kilogram and kilojoules per kilogram Kelvin. Okay, so we can calculate our change in enthalpy and get Q, and then at the same time, for B it wants to change in entropy. All right, so we'll go ahead and calculate S2 minus S1 as well. Okay. So let's do it. So if I come over to MATLAB, so let me bring this up. Okay, I'll get a new script. Okay, and so let me just make a note, kilojoules per kilogram. So H1 is 2875.5. H2 is 251.15. Okay. Now for entropy, that's kilojoules per kilogram Kelvin. S1 is 7.8356. S2 is 0.8312. Okay, so calculating Q. So Q is just H2 minus H1. And then DS, I'm going to call this DS system, is S2 minus S1. So let me save this. And then we can run it. Okay, so we're using SI units here. So we get that Q is equal to negative 2.6243 times 10 to the 3, so that's 1,000. So negative 2,624.3, and that'll be kilojoules per kilogram, because the units are the same as H. Okay, so let me box that in. And Q is negative, so that's going to correspond to heat removed from my system. All right, so just as we have it here, right, it's going to be heat removed from my system. Then S2 minus S1, which I'm going to call delta S of my system. S2 minus S1 is negative 7.0044. And that's going to have units of kilojoules per kilogram Kelvin. Okay, beautiful, beautiful. All right, so I have Q, which is my change in enthalpy. I have my change in entropy for the steam. And now we're asked, what is the entropy generation? All right, we've got this. Okay, so in terms of entropy generation, okay, if I think back to chapter 4, all right, S gen is going to be equal to delta S of my system plus delta S of my surroundings. Okay. So I know delta S of my system, I just calculated it. So what about delta S of my surroundings? Okay. Well, I'm going to assume that my surroundings can be treated as a bath. So that's equal to the entropy change of my bath. And that's going to be equal to Q bath over T. Okay, where Q bath, all right, the heat, in this case, heat absorbed by my bath is going to be equivalent and opposite in sign, all right, of the heat rejected by my system. All right, the heat rejected by my system is going to be absorbed by the bath. Okay, negative sign, right, because I need to switch the sign because what's rejected by my system is absorbed by my bath. So this will be negative Q over T bath. Okay, so S gen then, right, it's going to be equal to delta S of my system, which was S2 minus S1. Okay, and then it's going to be a minus Q over T bath, all right, where Q is actually H2 minus H1. So this could be a minus H2 minus H1 over T bath, where the temperature of my bath was equal to 30 degrees C. So I've already tabulated entropy. So let me just get T bath here. So T bath is 30, but I'm going to add to it 273.15 to get the temperature of my bath in Kelvin. Okay. And so then to calculate S gen, okay, S gen is S2 minus S1 minus H2 minus H1 divided by T bath. Running, I get an entropy generation of 1.6525. So S gen 1.6525. Okay, that's going to have units of kilojoules per kilogram Kelvin. Okay, cool. But again, this is essentially just delta S system minus Q over T bath, where I just plugged in H2 minus H1 just for completeness. My entropy generation is possible, which makes sense for this irreversible process. Okay, I hope that helps. If you have any questions, please let me know.